In this video, we're going to go over another equilibrium problem where using a rice table can help you calculate your answer. A 3 mole sample of pure NaCl was injected into an evacuated 10.5 liter vessel. After equilibrium was reached, 28% of the NaCl had dissociated. Calculate the equilibrium constant. Okay, like every other question so far, let's start by constructing a rice table. We'll reproduce the reaction to focus on the multiple ratios, 2 NaCl's yielding 2 NOs and a Cl2. All right. Now we weren't given any concentration or partial pressures to put into our ice table, so I need to find a way to find one or the other. I'll remember that my molarity formula is moles over liters, and that I've got PV equals nRT in my back pocket. Technically, we have the information for either one of these, either concentration or partial pressure. But I'm going to choose to do all of my math in molarity because the question is asking for the equilibrium constant, not the equilibrium pressure constant. Okay, so let's do a quick calculation. We're going to take that 3 moles of the NaCl and divide by the 10.5 liter container to get 0.286 rounded. Now I'm going to keep that number stored in my calculator for calculations later. And I'm going to put that value in the I box for the NaCl. The problem also states that the vessel was evacuated beforehand, so I'm going to assume that I'm not starting with any products. Okay. This is where things get a little different from before. We're not given an equilibrium constant or any equilibrium concentrations to puzzle out what's going on. So I need to use one of my other clues. I'm told that 28% of the NaCl had dissociated. That means where I would usually be writing minus 2x plus 2x and x, I really just need to multiply my numbers by the 28% dissociated. So I'll do a little bit of math on the side. 0.286 times 0.28, using those previously stored answers, gets me a change of 0.08 molarity. So I'll put those in my change boxes. Again, we use the percentage to figure out the change. Subtracting 0.08, adding 0.08, and then refocusing in on those mole-to-mole ratios. These first two guys have a 2 in front, but the chlorine has a 1. So I need to half my 0.8 to get the change for chlorine. Now that I know how much each of my chemicals is changing by, I can add up the I and the C rows. This is a great moment to reread the question. I've been in autopilot mode, searching for equilibrium concentrations, but the real question is the equilibrium constant. So let's write out the equilibrium expression so we don't make any errors in our calculations. The equilibrium constant is equal to the products, or rather the concentrations of products, over the reactants. I always take the time to write out my equilibrium expression to make sure that I don't make any errors. Okay, now let's substitute in our numbers. we will end up with an equilibrium constant equal to 0.00603. You can use this method every time you come across a percent dissociation, percent yield, percent ionization, percent anything kind of question. Even if you're given numbers that start at equilibrium and you have to find the initial concentration. And as always, make sure that you practice plenty of these.